Hey everyone. In this video, we're going to be talking about the cyclic structure of sugars. And so to get into the cyclic form of sugars, we have to talk about hemiacetal functional groups. We have to talk about alpha and beta anomers. And then we have to talk about Haworth projections to draw the cyclic form of sugars. And so your learning objectives for this video are to be able to convert a Fisher projection into a Haworth projection and to identify the alpha and beta forms of the cyclic monosaccharides. So let's get started. A functional group that you did not learn about in chapter 12 and 14 are hemiacetals. And so when an aldehyde reacts with an alcohol, it forms what's called a hemiacetal. Okay? And so a hemiacetal is sort of like an ether and an alcohol attached to the same carbon, but we give it a special name, and that's an hemiacetal. Now, what's happening essentially here is this oxygen is attaching to this carbon here, and this oxygen is going to pick up the hydrogen. And so the hydrogen shuffled over, and the OR is now attached directly to the carbon. So this is known as a hemiacetal. Now, the reason I bring this up is because hemiacetals can form within the same molecule. So if we have one compound that has both an aldehyde and an alcohol, you can coil it into a ring, and the alcohol here will attach to the carbonyl, and the hydrogen will get shifted onto that oxygen. And it forms what's known as a cyclic hemiacetal. So it's a hemiacetal formed within the same molecule where the alcohol and the aldehyde reacted together. So one molecule forms into a ring. And this can happen spontaneously if this is dissolved in water. And it typically only happens for 5- and 6-membered rings. Now, this carbon here, the hemiacetal carbon, is technically a chiral center now. And so when we close the ring, we're creating this new chirality center. And chiral centers can be either L or D, as we talked about in the previous video. And so you have a 50-50 chance of forming either the L or the D when you close the ring. And so the carbonyl that turns into an OH can end up either pointed down or pointed up. And so the new chiral center here is known as the anomeric carbon, and it can exist in one of two stereoisomers. You can have the alpha form or the beta form. And that refers to the position of the OH. So if your OH group is down, we call that alpha. If your OH group is up, we call that beta. So the alpha form and the beta form of a cyclic hemiacetal. Now, sugars have the ability to form these cyclic hemiacetal structures. And so this carbon right here is the anomeric carbon. And so in this case, because the OH is pointed down, this would be the alpha form of this sugar. And so the most stable form for pentose and hexose sugars are actually cyclic hemiacetals. So even though we draw it as a Fisher projection, most of the time they actually exist as these ring structures. And the drawing of this ring structure is known as a Haworth projection. So Haworth projection is this method of drawing it in a ring. And the orientation of the hydrogens and the OH groups on each chiral center is unique for the different types of sugars. And so by the end of this video, we'll teach you how to draw sugars in this ring structure. So if we have a Fisher projection and we want to draw it as a Haworth, first thing we have to do is take our Fisher projection and tilt it over 90 degrees. And so if your OH is on the right side, like on carbon 2 here, when it tips over, now it's on the bottom. The OH was on the top. When you tip it over, it's still on the top, right? And so make sure your OH groups maintain the same orientation when you tip your sugar over. Once you've knocked it over on its side, you want to bend it into a ring or twist it into a ring. And so the alcohol on carbon 5 is the one that's going to end up closing the ring. And so carbon 6 will always end up pointed up. And the eventual structure that you're going to get is a 6-membered ring with the oxygen in the top right. And so this is the core structure for any 6-membered sugar ring. And carbon 6 will always point up like that. And so you'll always have 1, 2, 3, 4, 5, and 6. And this will always be the same core structure for any aldohexose. And carbon number 1 here is always going to be the anomeric position that's either alpha or beta. That's the anomeric carbon. Now, when we close the ring here, this oxygen is going to connect to carbon 1, and the double bond O is going to turn into an OH. And as we saw here, you can form either the alpha or the beta version. And that's the same when it's a sugar. And so when we close the ring, you can have the alpha version or the beta version. And so we name this by putting alpha or beta in front of the name. So if the open chain form was D-glucose, then we have alpha D-glucose or beta D-glucose, just telling you that it's in a ring and it's either alpha or beta. Now, because this is a reversible process, meaning the sugars can close and open, close and open, they form an equilibrium. And so your open chain form can close as beta and then open back up. And then maybe it closes again and it's alpha. And then maybe it opens up, closes again as alpha, opens up beta, right? And it's just an equilibrium, and it can go back and forth over and over and over again. And so it's not locked into an alpha or beta conformation. It's only temporarily in that conformation until it opens up again. And then it can form either one. And so all 3 forms are in a dynamic equilibrium with each other. The majority of the time it exists in the closed form. Less than 1% actually exists as the open form in any given point in time. Now, let's see if we can draw a different sugar as a Haworth projection. So let's use D-galactose here. So first thing we're going to do, we're going to tip it over 90 degrees and draw it on its side. So HOH2C. And then at the end, we've got C double bond OH. And it looks like there are 6 total carbons with 4 chirality centers. So 1, 2, 3, 4 chirality centers. I'm going to number my carbons. All right, now at carbon 2, the OH was on the right. So when we tip it over, that's going to be down. At carbon 3, the OH was on the left. So when we tip it over, it'll be up. Carbon 4, the OH was on that side. So when we tip it over, it's up. And carbon 5, the OH was on the right side. So when we tip it over, it's down. Okay, so there's my sugar tilted over. Now, because there's 6 carbons and it's an aldose, we know right off the bat that it's going to have this core structure with carbon 6 pointed up, right? So 1, 2, 3, 4, 5, and 6. Now, let me copy this. And we're going to draw it in both the alpha and the beta forms. Yeah. Now, in the alpha form, you're going to have the OH pointed down at the anomeric position. In the beta form, the OH is up at the anomeric position. Now the only thing we need to do is to fill in the OHs at all of the chiral centers. So carbon 2, the OH is down, so we need to make sure that we draw it down. Carbon 3, the OH was up, so we got to make sure that it's pointed up. And at carbon 4, the OH was up, so we got to make sure that it's up on carbon 4. And at carbon 5, there is no more OH because this oxygen here, this O and this H, is now this O and this H. When it closed the ring, it transferred its hydrogen over to carbon number 1. So there's no OH drawn off carbon 5 because it turned into this one that closed the ring. So these are our alpha and beta forms of galactose. Now, these examples that we've looked at so far were for aldo hexoses. So what happens when you have a keto hexose? It's a little bit different. Ketohexoses form 5-membered rings with 2 anomers. And so a 5-membered ring, you're always going to have your oxygen at the top of the ring. You're still going to have your CH2OH sticking up. So that's carbon 6, which means that's 5. This is 4. This is 3. And that means that the anomeric position is carbon number 2. And the reason for that is because the carbonyl in a ketose is at carbon number 2. And so that means carbon number 1 is going to be sticking off of carbon 2 like that. And so if the OH is down, this would be your alpha form. And if the OH is up, this would be your beta form. So either way, you've got a CH2OH sticking off on both sides. It's always going to be up for carbon 6, but carbon 1 could be up or down, depending on whether you're alpha or beta. So keto hexoses make 5-membered rings. All right, let's do a study check. Identify each of the following as an aldose or ketose and as the alpha or beta anomer. So what do we think here? Let's look at the first one. If I were to number my carbons here, that's carbon 1, 2, 3, 4, 5, and 6. And so it looks like carbon 1 is at the anomeric position, and it's a 6-membered ring. So this is definitely going to be an aldose. And we can see that the OH is pointed up. So that means that this is going to be a beta form. Now, if we look at the one on the far right, 1, 2, 3, 4, 5, 6. It's also an aldose because it's a 6-membered ring and the anomeric carbon is in position 1. But we'll see here that the OH is pointed down, which makes that the alpha form. All right, now the two in the middle. If we were to number these, we see that the anomeric position is at carbon 2, which means that this is a ketose. And because the OH is pointed up, this is going to be the beta form. And this one here is also a ketose, since it's a 5-membered ring. And because the OH is pointed down, that makes it an alpha. Okay. So once again, if the OH on the anomeric position is pointed up, it's beta. The OH is pointed down, it's alpha. If it forms a 6-membered ring, it's an aldose. If it forms a 5-membered ring, it's a ketose. All right, so that's it for this video on converting Fisher projections into Haworth projections. Thanks for watching. I'll see you in the next video.